Hello everyone, I am Mansi Mahindru from ABES Engineering College, Ghaziabad. In today's lecture series, we're going to start with another application of greedy algorithm, that is single source shortest path. And inside the single source shortest path, there are basically two approaches that we're going to cover. One is Dijkstra algorithm and another one is Bellman-Ford algorithm. In this particular video, we're going to cover about Dijkstra algorithm. So let's start the video. So these are the basic contents that we're going to cover in this video. That is the shortest path problem, types of shortest paths, single source shortest path problem, about the Dijkstra algorithm and its time complexity analysis. So first of all, we have to understand what is shortest path. So in the previous video, we have talked about minimum spanning tree, and that is also one application of greedy algorithm. And another application is single source shortest path, where our main task is to find the shortest path from the source vertex to every other destination vertex. So in this, we have to find the shortest path from source to every other vertex. Right. So as it is written, the shortest path problem is the problem of finding a path between two vertices in a graph such that the sum of weights of its constituent edges is minimized. Now let's try to understand this with one example. So basically, before moving to the example, there are two type of shortest path, single source shortest path problem. Shortest path, the first type of shortest path problem is single source shortest path, and another one is all pair shortest path. All pair shortest path will going to cover in unit number 4, that is dynamic programming, and the single source shortest path we're going to cover in this particular unit under greedy approach. Okay, so in single source shortest path problem, first we're going to initialize our source node, and after that, taking that particular source node, we're going to calculate the shortest distance from that source node to every other destination node. For example, if my source node is A, if my source node is A, and I need to calculate the distance of A from every other route, every other route. For example, I want to calculate the distance between A and B. I'm saying shortest distance. So as you can see that there is one direct edge going from A to B, and its distance is 10. So means I can take edge A, B, which will give me cost as 10. But is it a shortest distance, or is it a shortest, or you can say a minimum cost that I can bear on this particular route? No. As you can see here, if I take edge A to E plus E to B, then I have covered this distance only at rupees 4. But in my previous path, I have invested rupees 10. So that means to travel from A to B, I have two possible paths, but the minimum one is A to E plus E to B. Likewise, we can calculate distance of A to E. Now, if I need to calculate the distance of from A to E, there is one direct edge going from A to E, which will cost me rupees 3. Which will cost me rupees 3. But is it a shortest, or you can say a minimum cost that I can bear, or some more paths are there to explore? So if I'll go from 10 to 4, no. This is the minimum that I can have on this particular loop. So this is my shortest path. So likewise, in the single source shortest path problem, we're going to take one source vertex and we're going to calculate the shortest distance from that source node to every other node. Now, in the single source shortest path problem, there are certain terminologies on which we have to focus. See, in this particular problem, you will going to get two type of edges. Edges can be of two types. One is positive edge and another one is negative edge. Edges can also be of two types, as well as you will also get question related to cycles. And cycle is again of two types. One is negative cycle, another one is positive cycle. Now, what is the difference between all these terminologies? Let's try to understand this with the help of example. As you can see here, in this particular example, you are you can observe that there are basically two type of edges involved. Like this is my positive edge and this is my negative edge. So in previous algorithm, in PRIMS, in Kruskal, that particular algorithm mainly consists of undirected graph as well as only the positive weights. But in Dijkstra and Bellman-Ford algorithm, you will going to get questions related to negative edge and you will get questions related to positive edge as well. So smartly you have to decide at which particular scenario you have to adopt which algorithm. So as you can see in this particular graph, there are two type of edges, positive and negative. And we can see this that there is a cycle in this graph. One cycle is this is C1 and this is C2. But while we are doing minimum spanning tree, our first step is to remove all the parallel edges and self loop because in the minimum spanning tree, it does not contain any cycle. But here, your graph may contain a cycle as well. So you have to take decision very smartly, like which algorithm you have to apply under which scenario. So now there are two type of cycles as well. There can be a negative cycle and there can be a positive cycle. Now, what is the difference between negative cycle and positive cycle? Let's take one simple example. Okay, by mistake, I have mentioned it minus infinity. Let's take some weight. Let's take it as 2. Let's take it as 5. Right. So now let's start with this. Okay, so we'll only cover cycle part because we want to understand what is positive cycle and what is negative cycle. So first of all, what we will do, we're going to take this will initialize our source vertex as 0 and all other vertex as infinity, likewise we did in Prim's algorithm. Again, we'll do the same thing. Yeah, but not now. For now, we'll not construct weight matrix because just we are trying to understand what is negative and what is positive weight cycle. But the question we have to do in the similar manner that we'll do in the numerical part. So as you can see here, if I start from here, 0 plus 5, 5. So 5 is less than infinity. So it's okay. C will accept my proposal and it will accept this 5. After that, this arrow is going in this direction. So 5 plus 6 is 11. 11 is again less than infinity. So it will also accept my offer. After that, 11 minus 3 is 8. So after this arrow is going in this direction, so 11 minus 3 is 8, but T is currently holding 5 value. So why it will accept my proposal? It will not. So directly you will come out of this loop and you will directly go here. So this is your positive cycle. Means cycle exists in the graph, but still you don't enter an infinite loop. You come out of that loop and you start working normally as your Prim's or Kruskal algorithm does. So this is called as positive cycle. Means cycle can be exist in the graph, but that cycle is not harming your particular question in any way. Is not harming your answer in any way. Right. But there is one more cycle. Let's see the impact of this cycle on our question. So as you can see here, one second, let me take a different pen. It's 0 plus 2. 2 is less than infinity, so it will accept my proposal. 2 minus 6 is what? Minus 4. Minus 4 plus 3. Minus 4 plus 3 is 1. Oh, sorry, minus 1. And minus 1 is less than 2. So it will be minus 1. It will accept. Minus 1 minus 6. Minus 7. Minus 7 minus 3. Minus 4. So as you can see here, this value is continuously decreasing and it has no end. I think it will get stopped at minus infinity and it will also get at stopped at minus infinity. There is no end. So what we face is we are stuck in infinite loop. We don't have any choice to move here. We have no choice to reach to our destination. No. So that is the impact of negative cycle. So if in your graph, if there is any negative cycle exist, then that particular cycle needs to be detected and it should be properly solved, right? That we'll see later how we're going to deal with this negative cycle. But for now we understand what is negative cycle and what is its impact. So this is your negative cycle. Now, there are two single source shortest path problem in your curriculum. One is Dijkstra algorithm and another one is Bellman-Ford. This video will cover Dijkstra algorithm and next video we're going to cover about Bellman-Ford algorithm. So, as I already told you, that Dijkstra algorithm is the algorithm where we are given with one source vertex and from that source vertex, we're going to find the shortest path from every other vertex. But the problem with Dijkstra algorithm is it it don't work on negative weights. Why it don't work on negative weights? Or it never worked on negative cycle as well. Because if your graph contains negative cycle, then Dijkstra algorithm has no role, has no solution of finding that negative cycle. That will see. That will see how Dijkstra algorithm behaves when graph consists of negative cycle. That we'll see later in the slides. But for now, let's first understand how to solve Dijkstra algorithm numerical if you'll get in your exam. So this is the algorithm. This algorithm we'll discuss after some time. Once we'll be able to solve the numerical, then we'll start. Right. So initially, like a Prim's algorithm will solve this numerical. So in Prim's algorithm, the first step that we follows is we have initialized all the values as infinity and we have created one weight matrix and that weight matrix will keep track of three things, that is Q, or you can say vertex V, key values and their parent value. And similarly, we have done in this particular question, we have taken record of all the vertices, the key values, and the pi value, which is the parent value of all the vertices. Now, after that, we have to start our journey from somewhere. So let's take our source vertex as S. So this is my source vertex. Now, after this, what I will do, I have to reduce or I have to decrease the source vertex to 0. So as you can see, this weight matrix, I'll reduce it to 0 and all other vertex remains same. Now, in Prim's algorithm, after this step, what we do? We used to extract the minimum vertex from this weight matrix. As in, we can say here that S has key value 0 and while other vertices contains key values infinity. So we're going to extract S from this weight matrix. Let's extract this. We'll extract this. Now, once we'll extract this, let's do all these updation in the weight matrix. So from this extraction, we came to know that now we are visiting S node. So let us mark this particular vertex and the node which is already visited or which are about to visit it, we have to copy all their values from the previous weight matrix. So we'll take it like 0 and nil. Now we'll start exploring the S vertex. Now from S we can go to T and we can go to Y because this is a directed graph, so we have to look at the directions also. Only outgoing edges will be considered. So from S we can go to T and to y. Now, if we'll take this path, it will be 0. It will be 0. If we'll take this path, it will be 0 plus 10. That is less than infinity. So it will be 10. So for t, what we will do, we're going to write here 10 and its parent will be s. After that, it is next is y. So we'll see 0 plus 5. 5. So 5 is less than infinity. So we're going to take y and this is y and parent is s. Now from s, there is no other path we can travel. So we'll copy all other vertex value from the previous weighted matrix and just like write it like this: infinity, nil, infinity, nil. Now after that, oh, I'm so sorry, it should be 5. Yeah. After this, we're going to extract the minimum value from this weighted matrix, and we got to know that this is the minimum one. So we'll extract this, and let's do this updations in the weight matrix. As you can see, from this particular weight matrix, we have already visited S, so its value will be copied, and we are about to visit Y, so its value will also be copied from the previous matrix. Now, for y. Now from y we can travel to z, we can travel to x, and we can travel to t also. So let's start exploring these paths. So if we're going to travel from y to z, it is 5 plus 2, 7. Let's take another marker. It is 5 now. So it will be y to z, it will be 5 plus 2, 7. So 7 is less than infinity, so we'll update it as 7. Z will be 7 and parent will be 1. From y to x, x is currently holding value infinity and you are giving as 9 plus 5. 9 plus 5 is what? 14. So 14 is also less than infinity. So you can mark it as 14 and parent will be y. Now, after this, from Y, you can also travel to T, which is still unvisited. So 5 plus 3 is 8, and 8 is less than 10. So you can write it like this: T will be 8, and parent will be Y. So these all are the updations that we have done till now. After this, again, you're going to extract the minimum value, and we find minimum value as Z. So U will be Z. Now, again, let's do all these updation in the weight matrix. So as you can see here, you're going to write uh, the node that is already visited is S, Y, and we are about to visit Z. So its value will be copied. Y is 5, S, 7, Y. Yeah. Now we have to explore Z, right? From Z, we can travel to X, right? So we have only two possible options to go. We can either go to X or we can go to T. So we'll only look at these vertices. Rest of the vertex we will ignore because we cannot revisit them again. So here you can see from Z, we can go to X. Yes. So X is 7. Sorry, Z is 7. 7 plus 6. 13. So 13 is less than 14. So you will update it. So it will be 13. So at X, you will write here 13 and parent will be Z. And whether we can go from Z to T. Z to T. No, there is no path from Z to T. So we'll write it like this only 8y. Now we'll extract. U will become 8. Yeah. So let's take another weighted matrix. And let's take another marker, another pen. So now U becomes 8. And let's update this value in the weighted matrix again. Second, let me take pen. So it will be S is already visited, Y is already visited, Z is already visited, and now we are about to visit T. Sorry, I've written here 8. You have to write it here, write here T. It should be T. So minimum is T, so we'll take it T. So again, we are about to visit T. So you'll mark it as visited again, and you'll copy all these values from the previous matrix 0, nil, 8, Y, and it should be 5, S, 7, Y. Right. Now we'll only check for X from T to X. From T to X. Yes, we can go. T is has value 8 and 8 plus 1 is 9 and X is currently holding 13. So yes, we can update its value. Its value will become 9. Let's update this particular value and so this will become 9 and here also we'll do the same updations. This will become 9 and parent will be T. Then after this we're going to extract X and but there are no other options left to visit, so we'll mark it and we'll leave will our will heap will be empty and we'll terminate the while loop and we'll come out of that loop. Now, so this is basically the final weighted matrix that you got. And this matrix will going to tell you the single source shortest path. Means from S, what will be the shortest path to reach to T? Means from S to T, the shortest path is 8. From S to X, the shortest path is 9. From S to Y, it is 5. And from S to Z, it is 7. So this is the shortest path that we got uh, from this particular weighted matrix. So this is very simple question and we have done it in the similar manner as we did for the prints. So it will not be very difficult for you to learn. Now, so this is a matrix. Okay, so this is one more practice question that I have added in the video. Just pause the video and just take some time to solve this practice question. And I have also provided you the solution in the this video. So do solve this question by your own once and just check the solution from here. And if you find any difficulty, do mention in the comment box. We'll solve it for you. Right. So first we'll do the algorithm, and after that we'll move to the drawback of Dijkstra algorithm. So this is basically the algorithm of Dijkstra algorithm, and it works very much similar to the Prim's algorithm. As you can see, when we are when we have started with the numerical, the first thing that we did is we have let me take pen first. Yeah. So first thing what we did is we have identified. So in this algorithm, initially we have passed three parameters inside the function. The first parameter is the graph G, the weight matrix, and the source node. After that, we're going to do some basic initializations. And that initialization is calling one function initialize single source function. And again, when control will come on this function, it will search for the body of the function. And here it finds the body. So it is saying for each vertex V belongs to V of G, do some initialization means do set the key value of all the vertices as infinity, their parent as nil, and initialize source vertex as 0. So these, I don't think I have to explain it again. All these initialization we have done in Prims as well as in Dijkstra, so they are similar. So this particular step will take O of V time. Now, after this, once this initialization is done, then control will go here. And after that, what it is doing, it is basically creating one set S. In Prim's algorithm, we are creating set A, and here I have named it as S. So it will be creating one set S, and initially, by default, one phi element is being kept in this set. After that, what we are doing, we Once we create the weighted matrix, our next task is to extract the minimum value. For that, what we did is we have created one min heap, and this min heap creation will take O of V time. So these all steps I have discussed in detail in Prim's video. So if you haven't watched that video, go and first watch Prim's video. Everything will be clear to you in depth. So in this particular video, will not take each and every step again and again, right? So next is this particular while loop will be executed till our bin heap will get empty. So this while loop will be executed for each and every vertex. So this will take O of V time. After that, after that, we're going to perform extract bin operation. And we all know that this extract bin operation takes log n time as we did in binomial heap. So here we are performing it on the vertex. So it will take log V time, but it is nested loop inside this while loop, so it will take V log V time. Now, for after this, once you have extracted the minimum node, then you used to check for the adjacent vertices. You used to check for the adjacent vertices. And in Prim's video also, I have discussed that this particular statement can have two scenarios. One is for dense graph and another one is for sparse graph. So this particular concept I have discussed in detail in the previous video. You just go and watch that once. Okay. So this dense and sparse is nothing. It's a complete and incomplete graph. If I'm talking about complete graph, then for every vertex, all adjacent vertices are directly connected. So I can say if I'm at vertex S, so all other vertices are adjacent. So I can say this particular line will execute for V minus 1 time, and it is a nested loop inside this, you can say, while loop. So it will run for O of V square. After that, we are calling relax function. What is this relax? See, whenever we find any adjacent vertex, what we used to check? We used to check whether the degree, or you can say key value of the source vertex plus WUV means the edge ka weight is less than the key value of the destination vertex or not. As you can see in the numerical also, we did the same thing. See, here also, we used to check whether uh, whether 0 plus 10 is less than infinity. So if I have to write this thing in the form of pseudocode, what I will going to write? I will write it like this only. Na? If my edge one point is u and another endpoint is v, so I will write it like this. Na? Distance of u plus w means edge ka weight of uv is less than d of v. If it is okay, if the statement is correct, then only I will going to do all the updations. And those updations are only written here. If this particular statement is true, then I will update its U and I will update its parent value. The same we did in Prim's algorithm, but the difference is here we are also adding the distance from source vertex. So we are basically adding the distances. But in Prim's algorithm, we only used to consider the edge weight. But here we are also considering the distance of the source vertex, right? So this statement will be executed, and here we are performing decrease key operation, and we know that decrease key operation will also take log V time. And this relax function is also a nested loop. So we're going to run it for V square log V. So again, the same thing. Again, your complexity for Dijkstra algorithm will be O of V square log V or O of E log V. Same as Prim's. Means the justification for the algorithm for the time complexity is same as the Prim's algorithm. Now, after this, we're going to start with one drawback of Dijkstra algorithm where actually this Dijkstra algorithm used to fail. Now let's take one very simple example. You can see here, let's take one example. Mhm. Mhm. Yeah. Let's take this simple example and just try to perform Dijkstra algorithm on this particular graph. So initially what we're going to do, we're going to create the, let's take different colors pen so that it will be easier for you to understand. First, what we'll do, we'll initialize this as our source vertex, so its value will be 0. All other values will be infinity. We'll keep it on fast track because we know how to solve this. This will be infinity. So we're going to construct one weight matrix V. Next is D of U, and the next is pi. We'll construct one weight matrix. Here we'll write A, B, C, D. So here we're going to write 0, infinity, 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 and parent will be nil. Now we're going to extract A. So U will be what? We're going to extract A. So now it means we have to construct one more weight matrix here, and V, pi, D, and pi. So we'll write A, D, C, and D. So it will be now we are have about to visit A. So we'll copy this value from previous matrix, and now we'll start exploring A. From A we can travel to B. So 0 plus 2 is 2 and 2 is less than infinity. So we'll update this value to here. So it will write 2 and parent will be A. From A we can go to C also. So 0 plus 3 is 3 and 3 is less than infinity. So we'll write here this. From A we cannot travel to D. So we'll leave it as it is. And here we'll update as 3 and it will be not infinity to nil. Now again, we will extract 2. I'm so sorry. We'll extract B. We'll extract B and we'll do updations on the weight matrix. We'll write here B, D, pi, A, B, C, D, and A is already visited, so we'll copy it from here and we're going to start with B. So we'll copy this value also from the previous matrix. Now let's start exploring B. From B, we can only go to C. So C is 2 minus 6. That is what? Minus 4. Minus 4 is less than 3. So we'll do this. C will be what? Minus 4 and parent will be B. From B, we cannot go to D. So it will be infinity to there. Now we'll extract minimum, that is C. Right? B, A, B, C, D. The node that is already visited is A, B, and now we are go to C. So value will be copied 0 nil to A minus 4 B. From C, we can go to D, right? Minus 4 plus 1, that is minus 3. So minus 3 is less than infinity. So we'll write it like this. And parent will be C. Now we are done and we are only left with D. So we'll next we'll extract D, but there is no yet vertex left to visit. So we'll stop here only. So as you can see here, the Dijkstra algorithm has given that if we'll start our journey from A and if we'll go to B, the shortest distance is 2. From A to C, the shortest distance will be minus 4, and from A to D, the shortest distance will be minus 3. So, is it so? Is it true? Actually, is it true or not? So, let's try to do this particular question manually once. Let's erase this thing. Let's do it again. Let's erase it. Yeah. So as you can see here, we'll write again, we're going to write here infinity and 0, 0, infinity, infinity, and we'll only follow the directions. So as you can see here, we can go from A to B. So 0 plus 2 is less than infinity, so we'll update the distance. 2. Next arrow is going in this direction. 2 minus 6. 2 minus 6 is minus 4. Minus 4 is less than infinity, we can update. After this arrow is going in this direction, minus 4 plus 1, minus 3. So we can do this. Arrow is going in upward direction, so minus 3 plus 4 is what? 1. Again, we can update. Again, arrow is coming in this direction, so 1 minus 6 is minus 5. Minus 5 plus minus 1 is minus 4. Minus 4 plus 4 is 0. 0 minus 6 is minus 6. So as you can see here that we are stuck in infinite loop. So here Dijkstra algorithm actually fails because Dijkstra algorithm is incapable for detecting negative weight cycle in your graph. But as you can see, this particular graph consists of negative weight cycle, but Dijkstra algorithm has not detected this cycle. But when we did it manually, we find that there is a negative cycle and we got stuck in some infinite loop. So this is where the Dijkstra algorithm fails. And we used to say that Dijkstra algorithm will only work for the positive weights and a graph which do not contain any cycle. So this is the drawback of Dijkstra algorithm. This drawback will be overcome by Bellman-Ford algorithm in the upcoming video. We'll see it later. So these are the references.